Excellent Academy. For today, we're looking at another method of integration known as integration by parts. For integration by parts, we perform our integral evaluation using a formula. The formula for integration by parts is given by the integral of u dv is equal to uv minus the integral of v du. So here's my formula for integration by parts. When it comes to integration by parts, there are four major values I need. I need a value for u, I need a value for du, which can be got by differentiating the value of u. Also, I need a value for v, and finally I need a value for dv. So these are your four required values for integration by parts. Okay, we'll take an example and we'll see how this works. Let's say, for instance, we are asked to evaluate the integral of, let's say, x cos x dx. Alright, for this now, this x cos x, here's the x. So I'm integrating this with respect to x. X becomes my integral variable. So to solve this now, what I do is this: relate x cos x to what I have here. That means u, this is u multiplying the v. This is x multiplying cos x. So obviously, if I should match them up, u becomes x and then dv becomes cos x. So for this, I will say let u be equal to the first thing here, that's x. And also notice that u is multiplying the v and not just v. So if u is x, it means that the v equal to cos x. So also let the v be equal to cos x. If I've got u, to get the value of the u, I'll have to differentiate. So hence, if u is equal to x here, if I differentiate, I'll have that the u is equal to 1. So if I differentiate x, I get 1. Also, if I have that the v is equal to cos x, to get the value of v, I'll have to integrate. Hence, if I integrate the v, I'll get v. If I integrate cos x, I'll get sin x. So I've got my four major parameters. That's u, which is x, du, which is 1, dv, which is cos x, and then v, which is sin x. Alright, next up now, I will substitute. So substituting, I will substitute these values into my equation. Substituting, I have that the integral of u dv is equal to uv minus integral v du. So I have this. Alright, repeat the question. Here I have that integral u is cos x dx is equal to uv. U here is what? U is x, it becomes x here, into v. V is sin x in value, so x sin x minus the integral of v. V in value is sin x, so sin x into du. Du in value is 1, so I'm having 1 here. Alright, so this is after substituting. If I work on this, it will now be equal to x times sin x gives you x sin x minus the integral sin x times 1 gives you sin x. So I'm having x sin x minus integral sin x as my result of this. But I will not stop here because I'm still seeing an integral sign. Hence, I'll have to evaluate this integral. Now, also note that when it comes to evaluating this, I am integrating sin x with respect to the same integral variable here, which is actually the x. Alright, such that this now becomes equal to x sin x minus, if I integrate sin x, I get minus cos x. Becomes minus cos x. Alright, of course, plus c, which is the constant of integration, because after doing my final integration there's no more integral sign here. So you now put plus your constant of integration. Work on this. This is now equal to x times sine x gives you x sine x. Next one, minus minus gives you plus. Next one, you having cos x. Next one, plus c. So this is how we work on terms using integration by parts. So my answer becomes x sine x plus x cos x plus c. So that's like the result after using integration by parts. So we'll take a second example on integration by parts. But before then, let's consider this example. Let's say we're asked to integrate exponential 3x, something like this, obviously with respect to the x. If I should work on this now, for this case, I'll have to use integration by substitution for this case. For this, I will say let u be equal to 3x, such that if I differentiate, I will have that du all over dx is equal to 3 after differentiating this, such that the x here will be equal to du all over 3. And also, I will now have that the integral of exponential 3x dx is now equal to the integral of exponential, we set that 3x equal to u. This becomes u dot dx. The x in value is du all over 3. From here now, my constant term here is 1 over 3. So take the constant term outside the integral sign, becomes 1 over 3 integral exponential u du. Alright, so this now becomes equal to 1 all over 3. If I integrate exponential u du, I'll have exponential u plus c. From here, what we said u is equal to 3x, so my value now will be equal to 1 over 3 exponential u in value is 3x, then plus c. So I'm having plus c. So I have this as my answer. You can also rewrite it as saying this is equal to 1 over 3 times this gives you exponential 3x times 1 gives you exponential 3x all over 3 plus c. So I have this value. The concept is this: if I'm asked to integrate the exponential of a term with respect to the x, my final answer becomes the inverse of this term here. Of course, if I differentiate ax, I'll be left with a. So the shortcut is this: simply repeat this. That's exponential ax all over, differentiate the part. If I differentiate the part here, it gives me a, then add c. So that's like the simple concept here, such that if I'm asked to integrate exponential 3x dx, my final answer is easy. What you do is this: repeat this man or write this man here, it becomes exponential 3x all over, differentiate 3x gives you 3, add plus c, and this was the answer there. So the shortcut of integrating terms involving exponential is simply to write out this term as your numerator all over, differentiate the index or this part, and keep it as your denominator. One last example: if I'm asked to integrate exponential, let's say 3x squared dx, this will be equal to, write out this term. This term is exponential 3x squared all over, differentiate 3x squared, you get 6x. So all over 6x, and of course plus c. So this becomes like the answer to this question. So this is like a shortcut on how to integrate exponential functions. So let's look at how we can actually use the shortcut I just showed you to solving problems on integration. For instance, let's say we are asked to evaluate the integral of x squared exponential 3x dx. Alright, so let's say we are asked to evaluate this integral. What do we do? For this case, remember that our formula is integral of u dv is equal to uv minus integral of v du. Alright, so for this now, I'll call this u. So let u be equal to what I have here, x squared. Differentiate u with respect to x, I'll get that du all over dx is equal to 2x. Next up, I will say let v be equal to or let the v rather be equal to exponential 3x. From here, if I integrate this, I'll have that v is equal to, repeat this, that's exponential 3x all over, differentiate 3x, I'll get 3. So I have this one here. Perhaps we could take this as du instead of du over dx. So this is my du value. So substituting into the value into the integration by parts formula, I have that the integral of u dv is equal to uv minus integral of v du. Alright, so that's now equal to u is x squared, becomes x squared into v. V is exponential 3x all over 3 minus integral of v. V here is exponential 3x all over 3 into du. Du here is 2x. So I have this value. If I have to work on this now, this now gives you equal to, so x squared times this gives you x squared exponential 3x all over 3 minus, I'm having this as integral. So this multiplied this gives you 2x exponential 3x all over 3. So I have this. So the constant will now be, take out the constants. The constant here is 2 over 3. So this is now equal to x squared exponential 3x all over 3 minus, this is 2 over 3. So take out 2 all over 3 integral. I'm left with x exponential 3x. So if I take out 2 all over 3, what's left is x exponential 3x. So I'm having this as my result after substituting. The case is now this. This one also is still in the form of integration by parts. So I'll now perform another operation on integration by parts using this. So in this case now, my new u will be x. So picking the integral of x exponential 3x and integrating by parts, I have that for this, the integral of x exponential 3x for this, of course, with respect to x, that's x is my integral variable. So for this now, for this case, let u be equal to what I have here, x, such that the u is equal to 1. Also, let the v be equal to exponential 3x, such that on integration of this, the v is now equal to exponential 3x all over 3 using the shortcut. So I'll take this off. So if I substitute this, I'll have that we said the integral of u dv is equal to uv minus integral of v du. So this is now be equal to u. The value of the new value of u here is x, it becomes x into v. The value of v here is exponential 3x all over 3 minus the integral of v in value is this exponential 3x all over 3 times du. The u in value is 1, so times 1, yeah? Or dot 1. If I simplify this, this is now equal to x times this gives you x exponential 3x all over 3 minus this times 1 gives you itself, so it becomes integral exponential 3x all over 3. This is now equal to exponential x exponential 3x all over 3. So the constant here is 1 all over 3. Bring the constants outside the integral sign, becomes minus 1 all over 3 integral exponential 3x. So I can still evaluate this. So this is now equal to x exponential 3x, this all over 3, right? This all over 3 minus, I'm having 1 all over 3 into, if I evaluate the integral exponential 3x, this now gives you exponential 3x all over, differentiate this, I get 3, such that this now gives you a value of like 9, okay? Now, here's the thing. So if I work on this now, this gives you equal to, I'm having x exponential 3x all over 3 minus, so expand 1 times this gives you exponential 3x all over 3 times 3 gives you 9. Alright, so this value is my final answer after evaluating this integral. So the evaluation of this integral here gives this value. Hence, from my previous example, or from my major question there, the integral of my question was equal to x squared exponential 3x all over 3 minus 2 over 3 integral of this. Now, the value for the integral of x exponential 3x, this value is now equal to this. So in this case now, I will have to substitute this value back into this equation. Alright, so this value is now this. Take this off and replace it by this value. Okay, so I'll now have, so this one goes off such that in place of that integral of x exponential 3x, I will now have this value, that's x exponential 3x all over 3 minus exponential 3x all over 9. So I have this value. Okay, you can now expand this and then simplify. Alright, so taking this one off. So if I expand this, this is now equal to, I'm having x squared exponential 3x all over 3 minus 2 over 3 times this gives you 2x exponential 3x all over 3 times 3 gives 9. Next one, minus times minus gives plus, 2 times exponential 3x give 2 exponential 3x all over 3 times 9 gives 27, of course, plus c, which is the constant of integration. So here's like another example of integration by parts. For this one now, observe that for this example, I had to do the whole process of integration by parts using the formula twice to get my final solution. Alright, in some examples, you have to do the whole process 3 times to get the answer. Alright, so this is how you solve this using integration by parts. So let's take yet another example on integration by parts. So in the previous example, we looked at something of this nature, the integral of x cos x dx, and we said we would liken this to the integral of u dv, and we said u should be x and dv should be equal to cos x. But the question is this: in questions involving integration by parts, does it mean that u is always equal to the first term and then dv equal to the second term? No. In some cases, u could be the second term here, and the v could also be the first term. It's very much possible from the concept of the commutative law of mathematics, because they are multiplying. So irrespective of the order in which they are placed, you have the same result. So how do we know which term in any question involving integration by parts? How do we know which term should be equal to u and which term to take as the v? Now, usually when it comes to integration by parts, note that u is often the value of u is often number 1. U can be inverse trigonometric functions. So if I say inverse trigonometric functions, always take them as u. Example, if you have something like sine inverse of x, cos inverse of x, tan inverse of x, these should be taken as u. Okay. The second kind of terms to take as u are the logarithmic functions. All right. So u is always most of the times used as logarithmic functions. Examples of logarithmic functions include, let's say, log x, and perhaps ln x, or perhaps ln x plus 1. So these are also another set of functions we take as u. Also, when it comes to the kind of functions we take as the v is usually number 1. We usually take exponential functions, such as, let's say, exponential 5x, or perhaps exponential 3x, etc. So exponential functions are usually taken as the v. Another set of functions usually taken as the v are the trigonometric functions. So usually trigonometric functions are taken as the v. Usually also take trig functions as the v. Alright, so we use this to solve some problems. Let's look at one more example for today's class. Let's say we asked to integrate log x dx. So we ask to integrate this, what do we do? Now, usually when we look at questions involving integration by parts, you usually see two terms multiplying. But in this case, I'm having just log x and there is no second term. Now, if I have a log x, question is this: log x, will it be u or the v? We already mentioned that for functions involving log or logarithmic functions, we take them as u. So if u is log x, what then is the v? Of course, we know that you can express this as being equal to, same as saying integral log x times 1, of course, dx. So I will express this in this form, and then obviously the v becomes 1. Alright, so this is like the concept of solving this question. So if I'm to solve this now, I will say let we said u is equal to majorly the logarithmic function. So let u be equal to log x. If I differentiate this, I'll have that du is equal to, if I differentiate log x, I'll get 1 all over x. Next up, let the v be equal to this one here, that's 1. If I integrate the v, I'll get v. If I integrate 1 with respect to the integral variable, which is the x, I'll get x. Hence, if I integrate 1 with respect to the x, I'll get x. Substituting these values into my equation, I'll have, we said the equation is integral of u dv is equal to uv minus integral of v du. So hence, This will now be equal to, the value of u is log x, so it becomes log x into v. The value of v here is x minus integral of v. V here is x dot the u here is 1 all over x. So I have this. If I work on this is now equal to log x times x gives x log x minus integral of x times 1 gives x all over x. Simplify this, I'm having this is equal to x log x minus x over x obviously gives 1. Alright, if I work on this now, this will now be equal to x log x minus, if I integrate 1 with, of course, respect to the integral variable x, I'll have x. So it gives me x plus c. And I have this, alright? So this is integrating 1 with respect to the integral variable, that's the x. So it gives x. So I'm having x log x minus x plus c. Hence, if I integrate log x, I'll have x log x minus x, then plus c, which is your constant of integration.